Good afternoon, and thank you. This is actually the one of a series of talks. Are we up? Yes, we are up.
Yeah, let's talk about
About the mill architecture. The mill is much too novel and complex to be summarized in just one talk, and this is a series. You are there on the cache hierarchy. Those ones which have already been done, including the one here that Andy mentioned, and our thanks to Stanford for asking us to come back. Those ones which have already been done are available on our website there, and this and future ones will also wind up being posted as well. The particular topic is cache access. There are a number of sub-issues involved in this. I'll be taking them one at a time. They are fairly independent of each other, but you'll see a common thread hooking through them. However, I must warn you that what I have to say will be a gross oversimplification of the way real chips actually work. I'm attempting to provide an intuitive understanding for people who are not specialists in the field. If you are, in fact, a specialist, you know that I am lying through my teeth. And please be patient with me and consider the intent and purpose. If you actually wish to get down into the bitsies, we've got bitsy answers for you, and feel free to ask about it later. The first topic is deferred loads, and I will explain that. But first, I must mention where we're coming from. This is not a research project. It's not an academic product. It's intended to be a commercial chip. Consequently, we must, in fact, wind up being driven by the marketplace. And what the marketplace wants out of a CPU is high execution throughput, low power, and cheap. Fortunately, how to provide that for at least certain kinds of programs has been well known for over 30, 40 years. First, your program needs to be wide issue. Your architecture needs to be wide issue. If you're going to have high execution throughput, you need to be able to have high parallelism and have a whole stack of instructions that are executed simultaneously. However, in addition, if you're going to have low power, you have to get all of the, what am I going to do next, get ready to do it next, do it, and then figure out what I'm going to do after that logic, which consumes 90% of the performance of modern general purpose chips like your x86 Haswells, for example. And coupled with static scheduling, you need to have an exposed pipeline for those two sort of come together if you're in fact going to wind up having a low power environment. You can buy chips like that today, most VLIWs, for example, and the mill works the same way. To explain those terms, the mill is wide issue, like a VLIW or the Itanium EPIC architecture. A single instruction actually carries multiple operations. How many the mill is a processor family, and how many a particular instruction can carry varies by the particular family member. Here, for example, the instruction carrying 3 operations. Those operations will be issued simultaneously. We only issue 1 instruction, but that means we're issuing 3 operations in this example. The lexical ordering within the instruction provides an ordering number for the operations, which are called slots. And slots correspond to functional unit pipelines in the execution hardware. Those pipelines are populated with functional units, adders, multipliers, floating point units, load store, what have you. But each one of the instruction slots corresponds to a pipeline, so that if you want to issue an operation to a particular functional unit, it has to be in the slot of the pipeline that functional unit is in. The operations are dispatched, torn out of the instruction, and sent to the individual pipelines, who then proceed to execute them. An exposed pipeline means that each operation has a known, statically known latency. When we start it now, we know that it's going to be done with its results available 4 cycles from now, 1 cycle from now, whatever, but always known. Thus, for example, if we have that source code, a sum minus a product, well, the sum and product are independent of each other and can be executed in parallel, simultaneously. So the instruction for that is going to have 2 operations, an add and a multiply. That will, of course, wind up being linked to 2 functional units, an adder and a multiplier. And the dotted pink line there means a cycle boundary in this and future slides. So sometime after we issue the add and the multiply, we're going to have results which we're now going to want to subtract. So there'll be a separate instruction with a subtract in it. There may be other things as well, but there'll be a subtract for purposes of this code fragment and a corresponding functional unit. 1 cycle later, well, we've got a sum because an adder takes 1 cycle, but the multiplier isn't done yet. Multipliers are not 1 cycle operations. So things are still in progress. So we have to go for another cycle, and now the multiplier is done and it's got its result available. Those 2 results are what we wanted for the subtractor. So they flow into the subtractor, and that in turn gets us the result of our final operation. Now you notice the grayed out item there that says who holds this. That's a result which winds up being just held because we're waiting for other things to come out. But there's no really good reason to hold it. Instead, what you always really want is that you have your code so scheduled such that the producer's results come out just in front of when the first consumer wants that value. So what we really want is to do that, so that the multiply starts early because it takes longer, then the add, and then both results come out at the same time. They retire is the term for the operation completing, and it will wind up going down into the result available for the subtract, and we have a final result. This mechanism is called static scheduling with an exposed pipeline. The mill works that way. There are lots of other chips that work the same way, commonly in the embedded world, stream processors, lots of things. There's a catch. There's always a catch. The catch is the exposed pipeline only works if you reliably have a statically known latency for every operation, because we've got to get things put out in the right order so that the issue comes out and the results come out at the right time. Not all operations have got a fixed latency that is recognizable. If the latency is not statically knowable, then the compiler must assume the common case, which is typically the optimistic case. And if the compiler is wrong, then everything else, we have to stop issuing all other operations until we actually have that result. Well, we're a wide machine, so stopping all other issues may mean that we are stopping issuing tens, hundreds of operations that we otherwise could have done, but it doesn't work because the timing turned out to be wrong. Ouch. In practice, the only varying latency operation that matters is load. Now, to show a bit of the detail about what we do about it, this problem, I got to point out a little bit about the hierarchy. If you have a load operation and it hits in the top level data cache, $1, why, on most machines, that'll take 3 cycles or thereabouts between the load and when the value has gone to the cache, been checked. If you do translation, the translation has been involved, the value has come back. The hardware engineers who do processors put blood, sweat, toil, and tears into making that as fast as possible because it is on the critical path for all program execution. And they can get it down to 3 cycles for many architectures. If the value you want is not in the top level cache, in order to make it fast, they make the top level cache small, which means very frequently the value you want will not be there. There isn't enough room to keep all the values you want. So instead you go down one more layer to the second level cache, D2. That's bigger, but it also will take 10 typical cycles to get a value back out. If it's not there either, well, there may be still another layer of cache, but where you're seeing the pattern here, but eventually you'll wind up having checked all your caches, and you're going to wind up going to DRAM, and that can be 300 cycles, depending on exactly what it is that you hook up and how lucky you were with respect to the DRAM refresh logic. That is extremely painful if your program has to do that. This is the load problem. When you write, for example, an add, and then a load, and then a shift, and then a store. Well, that's your logical program. That's the order you want things to happen because these operations need the results of the operations in front of them. But what you actually get is an add, a load, a stall, a stall, a stall, for a change, another stall. And finally, the value came back and you can do the shift and the store and so forth. Every architecture has this problem. They all must address it. And the goal is to hide load latency. There is a general strategy which all architectures who attempt to address this follow. You essentially ignore what the program said, and you issue operations as soon as their data is available. You issue loads as early as possible, essentially as soon as the address is known, or even earlier. This is called prefetch. Then you find something else to do while you're waiting for the data. There are 2 strategies for finding something else to do. There's a hardware approach called dynamic scheduling. This is derived originally from the Tomasulo algorithm on the 36091. I see a whole lot of people around the audience who, like me, date from that vintage and know what we're talking about. On the other hand, if you look inside a Haswell, Mr. Tomasulo would find it very familiar in many ways. The alternative approach is a software approach, static scheduling, with exposed pipelines and delay slots. The hardware approach with dynamic scheduling, well, the hardware decodes ahead. It's looking at the instructions quite a long ways before when it actually executes them, and it buffers the instructions that it decodes internally. That buffer is called the instruction window, if you hear me talking about windows later. It tracks all of the operations whose data is not yet ready. When the operations do have their data available and the hardware to execute it is available, then it can issue the operations. And as operations retire, it updates those operations which might have been waiting for that result so as to make them known to be issuable as soon as corresponding hardware is available. This is a good way of doing things, which is why this laptop and most general purpose machines work this way. The good news is that the strategy can, in fact, hide latency, those 3 cycles if you happen to hit in the top level cache, and it can hide at least some of top-level cache misses. Mostly it can hide top-level cache miss. It can hide some second-level cache miss, although typically it cannot hide 300 cycles of a DRAM access. But it can do, essentially, it can hide everything that it can find anything else to do. Otherwise, it will stall. The bad of it is that it's got this narrow window. That instruction buffer is not very big. It can't be made very big for power and performance reasons. And it can only find its operations to execute, which have been decoded and are sitting in that buffer. There may be other operations in the program that it could have issued while it was waiting for the data, but it can't because they're not in the buffer. The truly horrible thing about it, however, is that it's extraordinarily expensive in area and power. The software approach. The compiler does all the work, not the hardware. It determines dependencies among operations. It can look at the entire program to do so, rather than just a narrow window. It schedules the producers to retire just before the consumer wants the data. It schedules independent operations to issue together, and schedules loads under the assumption that they will in fact hit in the top-level cache. It assumes a latency of 3 for those loads. The good side of that, cheap, low power, fast hardware. There's no window limit. It can look at the whole program. The bad, there's a limited load concurrency. I shan't go into details about that, but typically it can't have as many loads in flight as the hardware approach can. The ugly side of it is that if it's wrong and we don't hit in the top-level cache, we're not doing anything else. We're stopping issuing all operations, waiting for that value to come back. This is the load problem. Except that, in fact, this is not the load problem because there are, in fact, several different load problems. If you take that load problem apart, you'll see that there's quite a bit of different cases which are relevant and you need to look at if you're going to attempt to have a solution. The simplest case is the case that you can't do anything about. Some loads will always miss to DRAM. If your program does nothing except random accesses into a hash table, which is bigger than cache, you are going to be pulling them from DRAM every single time. 1, 300 cycles, 1, 300 cycles, 1, 300 cycles. There's nothing that you, the hardware or the software, can do about this. Some loads must wait for data-dependent addressing. For example, a linked list. If I want to chain down a linked list, well, I have to go and get the pointer to the next item, and if the linked list is in DRAM, that's a 300 cycle wait. I now have an address, I do another load, and another 300 cycle wait. An address, another load, another 300 cycle wait, and so on. There's been various proposals about putting logic into smart memory and putting logic out into DRAM. We're a commercial operation, and much as we would like Samsung to help us out here, Samsung is not willing to do this, and the research in this area is not working very well. No CPU as architecture has a good solution to these cases. We don't either. Excuse me. Different category of load problems. Some loads depend on control flow. Take this case. I'm assuming C familiarity to everyone. This means look at A, and if it's true, you don't look at B. If it's false, then you go look at B. If B is something that might fault or throw an exception because it's a wild address or something, but A is good, then you better not go look at A until you look at B until you've gone and gotten A, because the exception is in fact, not correct, and you should not be issuing the corresponding load. This is not a load problem. This is a speculation problem. Operations in most machines, there's a mechanism in which operations can be issued speculatively. The hardware does not know, the program does not know that the operation is ever really going to be used. But if we get it started early, so long as nothing bad happens, if it turns out that we might need the result, and we turn out we do need the result, then by starting it early, we're ahead, and if we didn't need it, well, all we wasted is a little power. The mill does do speculation. However, speculation is the subject of a future talk in this series. We can only fit so much into an hour. And if you are interested in hearing about that talk, you can sign up for our mailing list, which announces these talks at that URL. Another category, some loads come in related groups. A classic example is iterating over an array. If each element of the array, you want to do something that doesn't connect to anything else, just to that element, well, you can load a whole pile of them in advance and hide the 300 cycles of the first one. You'll have 300 cycles to get to the first one. But if you can have 300 of them out there, you can just stream the values in because the addresses are known. This isn't a load problem either. This is a prefetch problem. The goal here is to have everything started up and streamed ready for you to perform. The fact that it's done through a load operation is irrelevant. What you really want is a stream of data. And mill prefetching is, in fact, the subject of a future talk in this series. And you can, in fact, sign up for the mailing list, which will get you an invite to that talk. Now, we've eliminated a number of cases which are either nobody can do anything about or are different problems. So what's left? Some loads are collections not of related operations, not a bunch of related loads, but in fact are relatively independent. Thus, for example, A plus B plus C, we can load A and B and C simultaneously, and we hope that they all come back together. But if it turns out that one of them has to go to DRAM or two of them have to go to DRAM, we don't have to do 300 plus 300. We can only do 300 and have everything come back all together. So that's one case. Another case is where you do a perfectly ordinary load and it misses in the D-cache, top-level D-cache, but it does hit in the second-level D-cache, and because that's 3 cycles versus 10 cycles, it took you an extra 7 cycles you didn't anticipate, but you may have 7 adds or multiplies or what have you that you can be doing in the meantime. Second case. It's a way to hide unexpected delay of relatively small quantity of unexpected delay. Both hardware and software approaches may be able to find 7 operations to perform, but it's not going to find 200 operations to perform while waiting for a DRAM hit. Out-of-order hardware handles both of these cases and handles it very well, but only these cases. This is a quote I love. The dirty little secret of out of order is how little out of order there actually is. The source of this quote is Andy Glue, who some of you may know who he is, but he was responsible for the architecture of both AMD and Intel CPUs and is now at MIPS and invented one of the mechanisms, one of the 2 standard mechanisms for doing out of order in his PhD thesis, and is amongst the cognoscenti is a recognized wizard. No, he's at MIPS now. He's been at MIPS for over a year. Um, the mill solution is called a deferred load. We've given you what the background is. Now we tell you what we do about it. A generic mill load operation. You, of course, have an opcode, load. You have an argument, which is an address. The mill has got a bunch of address modes. There's nothing greatly surprising about that. There's a 64-bit base address, a up to 32-bit offset, and optionally a scaled index. So plain, so common. You also have to say how wide a thing you want. The mill supports 1, 2, 4, 8, and 16 byte loads, or vectors of each of those. And so you have to say what it is that you want. Here's where things get strange. There's another argument called the delay. This is the number of issue cycles which the hardware must wait until retiring the result of the load. If you put in 3, the hardware is required to return the result in 3 cycles. If it can't return the result in 3 cycles, you will have stalls. If you put in 7, it returns the result in 7 cycles. So the program is explicitly controlling the retire time. So the load issue is here. We do another instruction. We do another instruction. We do another instruction. And still a 4th instruction. And now that's where the load retires. The consumer can be in the following cycle. Its data is available there. How do we know that the data is going to be available? Because the load operation said retire is deferred for 4 instructions. Now to compare this against the usual way of doing things. When there's nothing to do but wait, we've got a load and there's no other operation which is available that can be done until we get the result back from the load. We assume that there are no independent operations available. Well, the static approach is going to have the load, and because the static knows that it's going to take 3 cycles, there'll be 2 no-ops in the code, because otherwise it doesn't know that 2 cycles have gone by. Typical VLIW will have no-ops in these cases. These are delay slot operations, I may mention. The dynamic case will issue the load. It doesn't need no-ops, but we're assuming that we hit in the top level cache, there will be 2 cycles of stall. The mill with deferred operations will issue the load. Because it's statically scheduled, it also has to say we're going to idle for 2 cycles worth of no-ops, and the retire is there. One difference between the static and the deferred form, despite the fact that all 3 have got the same performance, the mill no-ops in the encoding occupy no extra space in the code stream. Mill no-ops have 0 bits in nearly all cases. And if you want to know how that works, that was actually covered in the first talk that was given here last May, and the details are available at that URL on our website. You can go take a look at the video to see how it's done. Yes?
So, is that unfair because you have a 2 in the load that has to be represented?
Again, please?
There's a 2 in your load, the delay number.
That says we have to delay for 2 cycles.
That costs you some bits.
Oh, the delay costs you a few bits. Yes, that's true. But that's per load, not per delay slot. Now, so much for the case where we don't have anything else to do. Now, assume that there are enough operations to hide the D1 latency, and in fact that we hit in the D1. This example will assume that there are 5 independent operations available. The static case can only set 2 of them because the static will always have a latency of 3. But there are 5 operations, so it will schedule the load followed by 5 operations. The value will, in fact, retire between op2 and op3, but that doesn't make any difference because we've got other things to do, and the fact that it retired then doesn't matter or is irrelevant. The dynamic case, it's essentially the same thing. It has 5 operations to do. It will retire earlier than the 5th one, but it's going to be busy doing the other operations anyway, so the fact that it retired early doesn't matter. The deferred case is going to say, well, I've got 5 independent operations, so I will schedule my retire to happen after the 5th operation. And it will then perform the 5 independent operations. The value could have been retired earlier, but was not. It was retired after the 5th. All 3 have the same performance. Now we come to the case when things are different. Here we have those same 5 operations, but we miss in the D1. The static case, well, it schedules the load followed by the 2 operations that it knew about, but then it will stall at least 3 cycles, and perhaps more. The double yellow line there means an unknown number of cycles if we happen to go to DRAM. Eventually it will retire, but it's only actually executed 2 with a possible 5 at the point of retire when it picks up again. The dynamic case can do better than that. It can, in fact, get all 5 done before it has to stop and wait for the value to come from wherever the value is coming from and picks up with the retire. The mill, deferred encoding, will have scheduled all 5, will do all 5. At that point, if the value is not available yet, we too will wait, waiting for the value to come back, and we will, at that point, retire. So the deferred case is the same as dynamic in terms of timing, and both are better than static. Reordering of your code can give you more opportunity to hide these stalls. You manually can rewrite the program, or the compiler can do it for you, or the hardware can reorder operations, so long as program semantics are maintained. So, for example, if that's the initial code, and that actual code, there's an operation there to hide 1 stall, so there will be a second stall even if we do hit in the L1. But loads can be hoisted over prior operations. They can be moved. And like that. We now have 2 operations between the load and its consumer, so we're hiding 2 stalls. If we hit in the D1, there will be no stalling at all. In addition, consumers may be lowered over later operations. We now have got 3 in between the load and the consumer. That hides 3 stalls. There are constraints. You can't hoist a consumer over its producer, that you have to preserve data flow order. But you also have to look out for side channels. There's 2 important categories of side channels. One is that loads and stores can communicate through memory, and the other is operations can communicate through exception handling. If the program, it may be important that any exceptions are delivered in program order. I won't address exceptions. Exceptions are the subject of another talk. The problem of going through memory, this talk is about memory. The problem of going through memory is if loads and stores refer to the same address. Obviously, a load and a store referring to different addresses are not communicating and in general can be reordered. But if they go to the same address, well, you can't hoist a load over a store or you'll get the former value, where what you're supposed to get is the later value. Hardware knows whether it's the same address or not. One of the advantages of the hardware dynamic scheduling. The software approach does not know whether it's the same address. It can tell sometimes, but all too frequently it cannot tell because the two addresses may alias, they may overlap. And in the case when the hardware winds up finding that they don't overlap, but the compiler cannot prove that they don't overlap, this is called false aliasing and is a source of considerable inefficiency in pointer-heavy code like most of your C and C++. So, eliminate aliasing. Loads C memory as of a snapshot in time. All stores which take effect prior to that snapshot in time, it can see. All stores which take effect after that snapshot of time, as far as the load is concerned, do not happen. The mill defines that loads C memory as of the mill's retire cycle, not where the load operation itself is issued, but where it retires. The instruction load 7, yes, it means deliver the result after 7 cycles, but it also means deliver the result as it will be after 7 instructions. This gives alias immunity. Load issue may be hoisted over stores, including stores at alias, because the issue is irrelevant. The only thing that matters is the retire. If this is your original code with a load in the consumer down there at the bottom and a bunch of stores prior to it, there's the retire. And because there's no space in between the load and the consumer, there'll be a few stalls in there when we actually execute this code. Copying that over and modifying it. There's the same code, but now we're going to lift the load up, hoist it. Suddenly, we now have got 6 instructions that we can be operating on in parallel. And it does not matter if those stores are to the same address as the load, because the load is seeing memory as of the retire cycle. These are the same semantics and the same value loaded. Loads can cross control flow. It's important that the control flow, however, have the same number of cycles between the issue load and the retire. If I have an if-then-else, that diamond there is an if-then-else, and we did a load of 9 cycles, and if the then and the else are both 6 cycles, well, it doesn't matter which way the control flow went. What we're doing is we're counting the number of instructions issued, and we'll get the retire there 9 cycles after the load was issued. If, on the other hand, the then and the else have got 2 different timings, 6 versus 3, for example, if we go down the 6 side, well, we'll retire there. But if we go down the 3 side, we would retire there. That's not going to work. So instead, we define what we call pickup loads. A pickup load operation looks very much like a deferred load operation. You have an opcode, you have an address, you have a width, but instead of a delay, you supply a program selected name, which identifies this particular load. The load issues there. The example uses T5 for a name. There is an instruction, some number of instructions, and then we execute another operation called pickup with the same name. The pickup acts as the retire for that load. The load retires there. It's available for the consumer. It does not matter what control flow there was between the load and its retire, or how many cycles there was in between. We're not going to do anything until the corresponding pickup gets executed. The pickup load issues there. The retire is deferred until the matching pickup is executed, and we're done. The compiler strategy for getting this kind of code into a code stream is actually quite simple. Most wide issue machines use time reverse scheduling, and we do too. You schedule the code in time reverse order. You decide where the consumers are first, and then you schedule the producers for that, and then treat the producer as a consumer and schedule the producers for that, and so forth. So scheduling is done in time reverse order, though the resulting binary will be executed in time forward order. The schedules produce retire immediately in front of the first consumer of its value. You schedule the longest latency data flow internally to the compiler first. That'll give you your best code and the shortest overall latency. You hoist the load issue to immediately after where the address is produced. For many loads, the address is statically known, and you don't have to you can hoist it all the way to the top of the function, for example, if you're loading out of the stack frame. If it turns out that there's fewer than the minimum number of cycles in between the load issue and the load retire, you may have to add a few no-ops. And when you've got that, you figure out how many cycles there are in between the load and its retire, and that's the delay that you put in the corresponding load operation. This algorithm is straightforward, it's quasi-linear, and is real easy in the compiler. The trade-off, in out of order, well, you can hide parts of some misses, and parts of all the misses you can hide. It is immune to false aliasing, but you got complex and power-hungry hardware. Static scheduling, a misstalls instruction issue. You cannot resolve false aliasing, but you got simple and economical hardware. The mill, we hide the same misses as out of order. We are also immune to false aliasing, but we have simple and economical hardware. Now, I said when we started that we wouldn't talk much about implementation, but this needs at least a word or two about how those work on the inside. Each mill family member defines a number of retire stations. These are hardware units containing buffers. Let's assume that the family member has got that number of retire stations. The load operation, that load operation, will first allocate a station. It will then unpack the arguments of the load into the station. And there's a data buffer. In parallel with this, we send a request to the memory hierarchy for that width number of bytes at that address. In order to implement the fact that we are having data as of retire cycle, we have to see if there were in fact any aliasing stores while we're in the process of doing all this. So when a store functional unit handles a store operation, it converts that into a store request, which is sent to the D1. And there's your store functional unit. And there's the D1 that we're going to send to. Meanwhile, Any active retire stations are monitoring the stream of store requests, looking for aliases. There's probably some inactive stations, but the active stations are going to be looking at the store requests as they flow by. If they hit, that is, if there's a matching or overlapping address, the station discards any buffered data that it has and re-requests the load. That re-request will see the result of the store. Guess what? That's the semantics we wanted, that the loads see the results as of the retire cycle. And if in fact there is aliasing, and true aliasing is very rare in real code. False aliasing is unfortunately rather prevalent, but true aliasing is rare. But you look, and well, you got to reissue it, and that may take a little extra time. But people who do aliasing deserve that anyway. Those of you who are familiar with the insides of the way load and store buffers work on a superscalar will know about monitoring store streams. This mechanism is essentially the same implementation, except that there are substantially fewer retire stations than there are load and store buffers. When it reissues a request, that request goes down to the D1, and the value will go back up to the retire station, which is now still monitoring and may in fact need to discard its data and re-request it yet again, if it's unlucky. Retire stations get allocated by the hardware. The stations are frame local. Each function logically has its own set. Of course, they don't have a physical set. There's a fixed number physically. The physical stations are dynamically allocated. Loads from different frames may be in flight concurrently. So if that's a stack frame, and that green frame issues 2 loads, it will have allocated 2 retire stations, which may retire quite some time in the future. Meanwhile, we do a call, new stack frame. The new stack frame, the pink one, may do its own loads and allocate a couple of retire stations and do a call. Note these calls may be interrupts for it too. The blue one now does its own couple of loads. We've got a whole bunch of ones now in flight. But the blue one wants to do yet another load. It thinks it's got a full set of 8. It doesn't know that somebody else is using any of them. So non-local stations, that is non-blue in this example, wind up being spilled. We pick one, that pink one is now turned red, and the pink aspect of it winds up going to the spiller, which is a mill hardware state save engine, which is running in parallel with everything else that's going on. And the red has now been reallocated to blue. We only spill the address and the width and the delay. We do not spill the buffer contents. Instead, when the return happens, we reallocate a retire station and re-request the load. Consequently, we are able to prefetch across calls, because when that return happens, the original load may have gone all the way to DRAM, but in addition to returning a value we're not using, it will have loaded the cache line into cache. So effectively, it's acting as a prefetch. Fine print. There are, in fact, a few rare cases in which a hardware dynamic allocator can find things to do that the mill algorithm cannot find. It is an exercise for the student to figure out such an example. A hint is that these mostly involve cascaded load operations. They are, in fact, rare in code, but they do exist, and it's left as an exercise. On the other hand, because the mill is doing static scheduling, it's got a complete view of the entire program. and can find operations that can be issued in parallel, which the hardware unit, which is restricted only to the instruction window, cannot find. This effect is also relatively small. I'm sorry, I'm slightly deaf and I can't hear that at all.
With the delay when you spill a load.
The delay remains unchanged. You're only counting cycles within the frame that issued the load. We're not counting cycles within the called bodies.
So it's not correct to think of the delay as representing some sort of fixed point in the instruction space.
It's a fixed point with respect to the code of that function.
The call is one instruction. The call is one instruction, no matter how long the subroutine takes.
Yes, the call counts as one instruction. These two effects are both minor, and they're offsetting. So to a first approximation, the mill memory access is essentially equivalent in performance to the dynamic out-of-order superscalar, which this laptop uses. However, the power and area and complexity cost is vastly less. Another matter of fine print. Retire stations that are spilled across functional calls or task switch get reallocated and reloaded, I mentioned. The original load will, in fact, have brought the line into DRAM, typically, though it may wind up getting kicked out depending on how complicated that call was. And in fact, branch prediction logic can anticipate that in fact a return is going to happen and get the reissued requests started ahead even before the return happens. The branch predictor may be wrong, but that doesn't matter because we're just simply going to toss away the reissueds anyway. So much for loads. However, memory costs are not restricted to loads. There's a thing called a store miss. You'll excuse me. When a program writes to memory and the line is not in cache that it's writing to, traditional architectures have got two possible things they could do. They could take the new data and write it directly to DRAM. This is called write-through. Alternatively, they can issue what amounts to a load, a read to bring in the cache line, and then once the cache line is in, then they can simply update it as if it had been there from the beginning. This is called write back. Either way, that store has to be buffered. It occupies memory traffic and bandwidth, and it's a fair amount of arm waving and power cost within the logic to handle it. Not on a mill. On a mill, every byte in the caches is 9 bits long. There are 8 data bits and 1 bit that tells you whether the 8 data bits are meaningful, a validity bit. When you do a store, and you put a value into that byte, the store supplies the 8 data bits, and the fact that they've been stored into sets the valid bit. If you allocate a new cache line that has not yet been stored, all of the bytes are invalid. So, for example, let's say we're storing 8 bytes containing the first part of hello world. Now, that's not the actual store syntax, it's purely for illustration. And there's no cache line. Well, when there's no cache line, we will in fact allocate in hardware a cache line in the top level cache. And the X's there mean that in fact they're all invalid. That value now gets written. We now have valid data, 8 bytes of it, and the remaining bytes remain invalid. Now assume that there's an interrupt. Interrupts do a lot of code, and frequently their code will be enough to pretty much scrub your top-level cache, and the dirty data that's in the top-level cache will be moved down into the second-level cache, like so. Note that the validity has remained unchanged. It's still got 8 bytes that are valid and the remainder invalid. Now the interrupt is done. We're back to the main program, and we do another store for the second half of our hello world. Note that the address is now offset by 8. Well, there isn't any cache line for it in the top-level cache, so we allocate a cache line. And we write to it. We now have a line for this address in 2 different caches. These are 2 cache lines, but they refer to the same location in the address space. Once that's set up, of course, you may want to read the value back. So we'll do a load. And when you issue a load, the request actually contains, besides the line address, it contains a mask of the bytes that you want to return, derived from the length of the original request. So if we do a load and say that what we want is in fact offset into the value we just read, have written, well, we'll allocate a retire station. We'll create a request with a mask and send that request down to the top-level cache. The top-level cache will find the corresponding line, if it's there, which it is in this case, and see if there's any overlap between the valid bits of the cache line and the mask bits in the request. In this case, there are, and those bytes get returned to the retire station. Only those bytes. But notice we still have some green requests. We still have not satisfied our entire request. The remainder need to be passed down the cache hierarchy to look at the next level cache, where again, we wind up checking to see if there's any overlap between the valid bits in the line and the request bits. There is, and those values get returned to the retire station. Now all of the request bits are satisfied. We can simply discard the request. No need to go any further. Although if there were some still left, we would in fact go further, ultimately down into DRAM. A retire station is now satisfied, and the load can retire. Any line in this process that is hit, that supplies any valid byte, will automatically be copied up 1 level in the hierarchy. So in this case, we hit in both lines, in both caches. The D1 is already at the top of the hierarchy, but we'll copy the D2 cache line that we hit in up and merge its data. The rule for merger is that the top valid byte wins. It's the obvious way of doing things. As a result, it is impossible for the mill to store miss. Stores are always, by definition, satisfied in the top-level cache. We don't have store buffers. We don't have all of the arm wavings of write through. It goes directly to cache. Now, while this takes care of a fair amount of the problems of load and of store, by far the cheapest form of memory access is the memory access you didn't do in the first place. So let's take a look at some of those cases, and to do that I have to give you a bit of a picture of what the cache hierarchy looks like at extremely top level. There's a CPU core, of course, and it's got load store functional units, and it's got retire stations. And we're a Harvard architecture, so there's a data cache, and the load store functional units send requests to the data cache, and the data cache returns results to the retire stations. As a Harvard architecture, there's also an instruction side. There's for reasons which you can see if you look at our first talk on our website that was given here last May, we actually have 2 instruction caches, and there's even a microcache higher up. Irrelevant to this talk, but I needed to have it actually reflect reality. There's a shared level 2 where Harvard only at the top level. So all of those values may flow from the level 2 up to the respective level 1 caches. Below the level 2 cache, we're only level 2 in these examples. You could have a level 3 cache. That's entirely a configuration issue. The device controllers, which feed to and from the level 2 cache, and they are in turn hooked to a level of devices. So far, so commonplace. However, and I should mention that the actual organization is member dependent, but typical. One thing you may have noticed that are not mentioned here is translation and the translation look-aside buffer, which is present in your memory hierarchy. We do have a TLB. It's there. Those of you who are chuckling know that this is not where it usually is. In addition, we have something that most machines don't have called protection look-aside buffers. And there are, in fact, 2 of them, one on the data side and one on the instruction side. And they are there. The protection look-aside buffer is essentially a cache over protection control tables maintained by the operating system, just like the translation look-aside buffer is a cache over translation tables maintained by the operating system. Commonly, protection and translation is done together on a machine like this, but not on the mill. Because of this organization, the mill uses virtual caching rather than physical caching, and it uses the single address space model rather than having multiple address spaces. There's one statically global, shared by everybody address space. Everything within the blue dotted line uses virtual addresses. Everything within that blue dotted line uses physical addresses. Now, to compare the models, the traditional model, program addresses must be translated to physical addresses before they can be looked up in cache, because the cache uses physical addressing. So a load operation passes a virtual address to the TLB. The TLB turns it into a physical address, which goes to a cache, which return lines to the CPU. The TLB is doing both translation and protection. If the protection fails, you'll get a fault, a trap. On the mill, all the tasks you're using virtual addresses. There is no aliasing across tasks with the OS. So a load operation actually sends the request to 2 different entities. One, it sends directly to the cache. Translation is not required, and data gets returned to the CPU. Simultaneously and in parallel, it sends the same request to the protection buffer, and if the protection fails, we will get a fault, just like anybody else, but that fault is done in such a way that the data that would otherwise have been pulled never does actually get back to the CPU. It's done in parallel with the request in the cache. This critter, the TLB, is a bottleneck. Because it's squarely in the middle of the critical path, it is vital that it be exceptionally fast. Fast means high power. Fast means small. Consequently, TLB misses are commonplace. And, well, it's painful. The reason why it's used is for historical reasons. Back when there were only 32-bit address spaces, but computers started having multiple programs running whose cumulative total address space across all programs was more than 32 bits would hold, well, you're screwed. And the solution was to give each program its own 32-bit address space, distinct from the physical address space used, and translate everything from the program's own idea of what a particular address bit pattern meant to what the hardware meant by a particular one. That translation is the TLB. This is no longer relevant in a 64-bit address space. You can fit lots and lots of programs with lots and lots of stuff in 64 bits. The cost, it's the critical path, it's power hungry, it's small, so it has to be multiple leveled, and real programs, as opposed to benchmarks, frequently are spending as much as a quarter of their entire processing time dealing with TLB. Why put translation after the cache? Well, the TLB is out of the critical path. In particular, you're only going to go to the TLB if you miss in cache, which means that 95% of all the loads and stores are never going to go to the TLB. Consequently, it can be big, it can be low power, and if we're going to the TLB, it means we missed in cache, and what's going to happen next is a 300 cycle DRAM wait. So consequently, if we take a cycle or two extra to be economical in our TLB, well, 300 versus 302 cycles, nobody cares. A side benefit is that everybody has the same meaning for a given bit pattern in a pointer. Consequently, if you want to pass a pointer between programs, or most importantly, a pointer between a program and the operating system, the bit pattern means exactly the same for both sender and receiver. The two may have different permissions. One may say, I have the rights to use this bit pattern, the other may not. But they mean the same place. Consequently, you don't have to do any translation when you're sending these things across. It turns out that on many machines and many operating systems, the operating systems winds up spending a truly amazing quantity of time handling system calls that take pointers, things like reads and writes, and getting them translated to what the operating system thinks is the corresponding address. Not at all necessary on a Mac. Protection checking can be done in parallel. It's easy. Now, when we allocate memory, on a conventional machine, an allocation like a memmap, which is, if you speak Unix, when we allocate a megabyte, it does not actually allocate physical memory. What it does is it allocates address space. But it has to record the fact that it's allocated this, and the way it records that fact is it maintains a page table private to the operating system. And that page table is full of PTEs, or page table entries, one for each page, that says this hunk of address space is in fact been allocated. It belongs to this program. And because we haven't allocated any physical memory, we are saying that this page is unrealized. It's not yet backed by any physical memory. This is a good thing, because backing things by physical memory is expensive. But the operating system sets up its page table in memmap. When we do a store into this situation, bear in mind there's no physical memory again, that store is going to, the first time through, remember translation is in front of cache, so we can't look at cache yet. So we go to the translation look-aside buffer, the TLB. The TLB will not find anything in there, and so it consults the OS page tables, and it will find an entry in the page tables, and it will find that it is unrealized. It will then cause the store to trap into the operating system. There's no physical memory. Somebody's got to get me some physical memory because stores always will wind up going to physical memory, and the caches will use a physical memory address. The OS winds up allocating a physical page there, zeros it, which takes quite a long while because it has to go actually to DRAM for all of this stuff. You notice it takes a while. Updates the page table entry to the corresponding physical address. That's now turned green to indicate it's correct. Fixes up the page table entry and returns from the trap, and the store can now proceed. All is happy except for the person who is looking at the clock. On the mill, well, we don't create page table entries. Instead, by definition, any address space that is not covered by a page table entry is unrealized. The mem map, well, there's still a page table for those pages which have had places allocated for them. But the mem map allocates the address space, but nothing gets put into the page table. We now do a store. Well, remember, stores don't go to memory. Stores only go to the top-level cache. No involvement with the TLB. We don't have to find a page table entry. There's no associated physical memory. And the address space is backless. This is backless memory. Things that live entirely in cache, not in DRAM. There's never even been DRAM allocated. If, however, the program does a no-no and loads a value that never got written, it will miss in cache because it's never gotten written. So we issue a load. The load store functional unit does its thing. We will check to see if we have permissions for this area. The PLB will check and will say that it's okay. We will look in the D$1, the top-level data cache. Nope, no such luck. We'll then look in, this is the request flowing down that you saw earlier on. We'll look in the second-level data cache. Nope. We'll now find the page table entry, which involves looking in the TLB, just like anybody else. And when the TLB won't find it, but it'll look in the page table, and it won't find a page table entry either. There isn't one. At this point, without going to DRAM, we've got a retire station, the TLB returns a 0 directly. That is, a miss to backless memory implicitly defines that backless memory is already 0. We didn't have to allocate it. We didn't have to initialize it. We simply load miss into it. Oh, this thing is backless. Have a 0. The retire station has a 0. Up the value goes when it times out or the pickup happens. And away we go. There is no access to DRAM. The other side of accessing DRAM is an evict. Bear in mind the stores only go to the top level, but eventually cache gets busy and we wind up evicting dirty values that have to be written back. Well, that eviction, you will always pick a victim. That victim, of course, will be in the second level cache because that's things that get written out. So we select the least recently used line, standard algorithm, and let's say it's that line. We'll search for a page table entry. Guess what? There ain't one. So at that point, we have to allocate a physical page. We are, in fact, going to put things out into DRAM. We need a physical page. And let's say that that is the physical page which you allocate. We update the page table by adding a new page table entry, which refers to our new data, the physical memory. We copy the data to memory. We discard the cache line, the one we just evicted. And that cache line is now usable by somebody else.
Is that allocation of the main memory an OS function?
All steps are in hardware.
What happens in case of memory map input output? So if I store to memory map,
Save it until after the talk. Otherwise, I'm going to run into time trouble. I will answer. There are no traps to the OS. Fine print, of course. You knew there was going to be fine print. The way this works, the way the hardware is able to do it, is that we use a hierarchical page table, which is a common mechanism in which you have different sized pages. But uniquely, we support pages which are 1 line long. The hardware allocates out of a bitmap of a bunch of 1-line pages, which are all contiguous. Hardware allocates out of bitmaps real well. If it succeeds in running out of its bitmap, then the hardware will allocate from a list of available other blocks, which has got associated bitmaps. If it runs out of blocks, it triggers a trap. However, there's a background OS process which makes sure that the hardware's list of blocks is full enough that actually running out is a rare event. That's backless memory. And that takes care of many memory things, but not all of them. A large quantity of the memory accesses for everyone is stack frames. Probably the majority of all memory references for everything except high-performance computing and benchmarks. Many of those references are initialization, and much of that initialization is to 0. When a stack frame exits, all the lines in the frame are garbage. They are dead. But they will be dirty in cache. And if we don't wind up reusing the space of that frame, those will wind up being evicted back out to DRAM, even pointlessly, because they're dead. They're meaningless. Access to uninitialized data is a common bug. And a common exploit is to browse in the rubble left by exited stack frames. You look up in your stack, and there may be what was left of a frame that was doing password validation, and in the memory there is the password in clear. And if you just simply go and look there, you'll find things you're not supposed to. This is a common source of exploits. The implicit 0, you've got a data stack. Stacks grew up in this example. On the mill, you allocate a stack frame explicitly with the stackf operation. It takes an argument, which is the amount of space you want to have, and that is in units of lines. So stackf of 4 says, I want 4 lines worth of a new frame. Simultaneously, there is a bitmap, the implicit 0 bitmap, with 1 bit for each of these lines there. And we associate 1 bit with each of the new lines. These bits are clear, they're false. Now, if we do a load from an implicit 0 line, as for example in that case, we have a retire station, we send a request down there, it looks at the bitmap and it says, no, this has no data. it returns a 0. We didn't have to initialize it. You unconditionally will get a 0. You can't browse in rubble, you'll get a 0. If you do a store to an implicit 0, it writes the data. There's a store request. Writes the data. Sets all of the bytes of the rest of that line, remember it's a new line, to 0, and sets the bit. Subsequent loads will look at the bit and say, oh, this line has been realized, and we'll actually go and look at the cache hierarchy for the line. A return operation discards all realized lines in the frame that you're returning from. So we've got one realized line here that is there. We execute the return. That line is discarded. In the course of cutting back the stack, we reset so those lines are no longer part of the stack. We also reset the corresponding bits in that bit mask. The realized lines are discarded. In fact, what we wind up doing is we just simply clear all the valid bits. Consequently, they will not be written back to DRAM. We also clear the dirty bit. You knew there was going to be fine print. Compiler optimization can recognize the fact that things are being initialized with 0 and simply skip that instruction. You don't have to. It's going to be 0. However, this greatly confuses initialization error detecting tools like Purify or Valgrind. So those have to be modified to run on a mill so that they are aware of the existence of an implicit 0. Otherwise, they will give you errors all over everything. It could be used for other kinds of allocation. We do not. There's been some discussion about using it for the active allocation point in a garbage collecting system, but maybe someday. The bit mask covers all of the lines at the top of the stack, and obviously it rotates with the stack in the obvious way. Consequently, it may cover lines which cover more than one stack frame. A typical implicit 0 mask will be 64 bits covering the top 64 lines of the mask, which may be a number of different frames. As calls happen, the mask rotates, so it's always covering the top lines of the mask, of the stack. You could ask for a stack frame which is bigger than those 64 lines. In that case, all the ones which are not covered by the implicit 0 register are immediately allocated and initialized and realized by the stack of operation itself. It just generates the necessary numbers of dummy stores. A task switch forces realization of everything. There's complications of implicit 0 if you're running in a multi-core, because the memory does not reflect what the running core with the implicit 0 is going to see. If some other core has the ability to look at memory underneath it, it will see the values that should be 0 but are not because it's looking at real memory. The hardware has mechanisms to handle this. Multi-core is, however, a topic of another talk in this series, which we invite you to come and hear. Lastly, Memory consistency is an issue, whether you are taking a long time for your loads and stores or a short time for your loads and stores, because memory consistency leads to memory consistency bugs and frequently very painful and slow operations to ensure consistency. If the program says that, for an example, that's a semantic order. Whatever the program said, that is defines the semantics of the execution of the program, and the time order of execution defines the semantic order of the program. The mill is a wide issue machine, so this turns into instructions, and let us say that both loads and the store were wound up being put into the same instruction, which they could be. And there is a semantic ordering in slot order for the wide issue. It is the compiler's job to make sure that it encodes the operations in the slots in the same order as the program is specified. So we know that the slot 0 load must be the load 1 on the left-hand side, because it has to be before the store. And the load in slot 2 on the right-hand side must be the one, load 2, which is after the store, in order to preserve semantic ordering. Now, we now have semantic ordering within an instruction. That instruction winds up being distributed out to functional units during decode, as explained at the very beginning. And those wind up going out to the functional units in slot order. Consequently, we are now defining a semantic order within the functional units as they execute. In fact, physically, they may be running in parallel, but the visibility between units is ordered in that same semantic order. Those functional units issue requests. Those requests will wind up going down to cache, and request defines a request order, which is also the same semantic order as from the beginning.
But the loads are as of the retire, not as of the instruction.
Quite true, and if I could put all of that on a slide, I would. There is a defined order. Take it after I finish. I'm soon to finish. Okay? So we have a defined order here in the cache, and it may get satisfied and things may go down further, but they too will wind up retaining the order. Consequently, top to bottom, from the original program all the way down through instructions, functional units, requests, and data, there is no overtaking. Nothing is done out of the original order. This is called sequential consistency and is universally regarded as the most intellectually understandable memory model and organization, but it only applies within a monocore, within a single core. There are no membar instructions, which are commonly required if you do not have hardware sequential consistency. Membar is extraordinarily expensive and very, very hard to get right. There are no memory erase bugs. If you are in fact running in a multicore, you have a cache coherence protocol. Multicore is the topic of another talk, and one of the aspects that will be covered in that talk is the fact that our cache coherence protocol merges the sequential consistency of each core into a globally sequentially consistent ordering across all cores. How it does that is 15 minutes with the slides, so you won't get it today. However, interestingly enough, due to other aspects, some of which were touched on today, The resulting cache coherence protocol runs at roughly twice the speed of the cache coherence protocol on a conventional, and cache coherence protocols on a high count multi-core can consume an awful lot of your performance and power. You can sign up at that URL for an invitation to that talk. Summaries. It'll hide cache latency and cache misses to the extent that it can be done, because there are, in fact, operations. So the performance is like out-of-order hardware, and the power cost is like static scheduling. It is immune to false aliasing. It will implicitly prefetch across interrupts and function calls. Doesn't need to zero initialize stack frames. Doesn't write back dead frames. Prevents uninitialized frame debugs. Has no store buffers, as opposed to 50-odd on something like a Haswell at extraordinary cost. Stores go to cache directly. Eliminates the great majority of TLB references. Shared address space simplifies the operating system. Backlist data needs no physical pages. If you allocate a hunk of memory, use it, deallocate it. There may never be any memory at all, and the OS is never involved. Uniform sequential consistency throughout. I think, didn't I mention that you could sign up? Thank you, folks.